My name is Brian, and in this video, I'll be presenting our paper titled JDT3D, Addressing the Gaps in LiDAR-Based Tracking by Attention. Most tracking approaches follow one of two paradigms, tracking by detection or joint detection and tracking. Joint methods have some key advantages over TBD methods, namely that they can leverage temporal information to help detect objects with weak visual cues, and they can leverage appearance, position, and motion cues simultaneously to learn a more generalizable shared representation. In our work, we focus on the tracking by attention approach to joint detection and tracking, which leverages the attention mechanism of transformers to perform tracking implicitly and represents objects as query vectors that are passed from one frame to the next. Even with these expected benefits of joint methods and tracking by attention, tracking by detection methods continue to achieve state-of-the-art performance on LiDAR-based benchmarks, such as new scenes as shown here. Recent works have begun to explore the potential of tracking by attention, although the gap between the state-of-the-art and tracking by attention remains. In our work, we identified two key gaps holding back TBA methods in the LiDAR domain. First, object sampling augmentation used by single-frame detectors cannot be directly transferred to the sequential training of TBA methods. To address this, we propose an extension that we call track sampling augmentation that achieves dense scenes that are still temporally consistent. The second gap is that existing TBA methods often inconsistently handle queries in training and inference. In our work, we show that by switching to a confidence-based query propagation during training and inference, we can achieve improved tracking performance while simplifying the pipeline. To achieve joint detection and tracking, we build on existing transformer-based 3D object detectors to create our LiDAR-based JDT method called JDT3D. At each iteration, a LiDAR point cloud is passed to the feature extractor to obtain a bird's eye view feature map. A heat map is used to estimate potential object locations in the scene. The heat map's peaks are used to initialize a set of proposal queries indicated by the multicolored boxes. These proposal queries are passed to a transformer decoder layer that generates one prediction for each input query. The queries that are decoded with a high confidence are passed to the next frame of the sequence as track queries, or TQ. These track queries are appended to the proposal queries in the next frame and passed to the transformer decoder altogether. Track queries predict the new location of previously seen objects in the scene, while proposal queries only predict untracked objects, birthing new tracks. This cycle continues for each LiDAR point cloud in the given sequence. Next, I'll discuss the track sampling augmentation and the confidence-based query propagation. To extend object sampling augmentation to our sequence training, we inject subsets of tracks from different scenes into the point cloud sequence, as shown in orange on the right. This is accomplished by appending the LiDAR points of the injected tracks into the point cloud of the scene. A collision test ensures no overlapping objects. The faded boxes in the figure represent positions of the objects at previous time steps. Because this is performed over a sequence of frames, the injected tracks are temporally consistent. To address inconsistencies between training and inference, we use a confidence-based threshold for both training and inference, unlike previous methods. This naturally creates varied queries during training, such as false negatives and false positives that need to be handled accordingly. Query augmentations that simulate these false negatives and false positive cases are no longer required, which overall simplifies the pipeline. Based on our tracking performance on the new scenes test set, we show that JDT3D outperforms existing LiDAR-based tracking by attention methods across all metrics. However, even with our improvements, tracking by attention methods continue to lag behind baseline LiDAR-based TBD methods. Analyzing the metrics, we attribute the gap in the A-moda to be the high number of false positives. This indicates that JDT3D has difficulty initializing new tracks. We performed ablations on the amount of track sampling, showing that just using a fraction of the baseline amount of track sampling, we can see significant improvements across all metrics. Below, we show a graph of the training curve over 20 epochs, showing the significantly improved convergence rate when using track sampling. We also perform ablations comparing both query propagation methods during training. showing that using confidence-based query propagation outperforms the previous matching-based propagation criterion. In addition to ablating on JDT3D, we performed the same ablation on PFTrack, a camera-based tracking by attention methods. These results match our findings on JDT3D and support our conclusion to switch to the confidence-based query propagation. Thank you for listening.